All right, can everybody see my screen?
Yes.
Okay, thank you. Thank you for that introduction. Good morning, everybody, or good afternoon, depending on which part of the world you're in, or even good evening. My name is Vic Mahays. I recently graduated from Howard University Department of Bioinformatics, Computational Biology. My specialty is dealing with calculating protein stability, protein-protein interactions within the verified protein structures, which we downloaded from the PDB, the protein database website. So for this research paper, what we did, we were comparing the stability with the ACE2 receptor in SARS-CoV-1 spike protein and SARS-CoV-2 spike protein. We also show preliminary receptor binding affinity, differences between both, and the results in addition to the conclusions. I would concentrate the conclusions on two specific ethnic groups. One is the Latino Americans, and the other one is the African Americans, where we saw a few mutations that were highly destabilizing the protein structure. Now, just a background on angiotensin converting enzyme. It serves really a few roles in the body, particularly inside the lungs. I will pay attention to. It regulates the vasodilation, protects endothelial function, and inhibits the inflammatory response. Now, on the flip side, if you look at the ACE2 disruptions by the SARS-CoV-2 protein, you will see that in the same lung tissue, it causes bronchitis, pneumonia, and respiratory distress. This is also related to the what they call the cytokine cascade, where it starts in the lungs and it starts to attack. Like your immune system is revved up and it starts to attack the immune system in hopes of destroying the virus, but at the same time, the cytokine cascade is leading to sepsis. So in the long run, most patients, they die of comorbidities associated with the infection of COVID-19. On this picture here, what you're seeing is this is the S protein trimer. It's a trimer because we have the S1, the S2, and also for this model, we bind with the glycan. Now the glycan, which is right here, when it interacts with the SARS-CoV-2 ACE2 complex, it creates what we call here an RBD, receptor binding domain. Now within the receptor binding domain, this is where the S1 latches onto the ACE2 receptor. And from there, it allows us to get inside the cell. Inside, for this particular protein structure, as I said, I am specifically looking at the ACE2 SARS-CoV-2 S complex. So this is the ACE2 COVID-19 complex. But before I get into the computational and the mathematical results, I would like to share with you the real foundation of protein stability, and particularly inside my lab, what we study. Well, yes, in protein fold, see, when proteins fold, it attains the lowest energy conformation possible for its function. Now, the change in free folding energy is used to quantify the magnitude of a protein's effect on stability. In general, effects on protein stability is in two distinctive categories. One is destabilizing and stabilizing. So what you see here is entropy, which is disorder, the naive state, the native state of the protein has the most disorder, but as the energy increases and also entropy, you have the unfolded. Now, in the unfolded, you see a lot more mutations going on. The reason is because you have unfolded the protein and you also have exposed this hydrophobic core, and that's very bad for an unfolded protein. We designed a workflow procedure in our lab based on command line, Python, Perl, and R programming languages. Our approach is we would take the download the structures from the protein database, in addition to looking at two other databases for mutations. The HGMD is a downloadable mutation database that shows mutations that were actually clinically tested, particularly inside different ethnic groups. The DBNSFP stands for the Database of Non-Simultaneous Frequency of Proteins. Now, this is really a theoretical, the DBSNFP, and this is more, I would say, real world. So the reason we use both is to try to compare and see if the values we obtained for the mutations are in both databases, and also in specifically different ethnic groups. So as I said before, we download the ACE2 SARS-CoV-1 versus SARS-CoV-2 complexes. SARS-CoV-1 is what they call the parent of SARS-CoV-2. SARS-CoV-1 around 2001 to 2003, it caused about 50 to 75 deaths in the United States. Now, what happened, we call it the parent, and why we call the COVID-19 the child is because the child of the ACE2, the SARS-CoV-2 virus, has a binding affinity for the ACE2 receptor greater than 10-fold. So the COVID-19 actually binds to the ACE2 receptor very strongly, and the infectious rate, as you can see during the year and a half, 2 years of the pandemic, it caused a lot of deaths. So in another how can I say this? Another project I'm doing is I'm tracking the evolutionary changes from SARS-CoV-1 to SARS-CoV-2. And also I'm doing a full study on the SARS-CoV-1 to SARS-CoV-2 in addition to Omicron. So hopefully I can predict some future mutations. Down here is where it gets very technical. Foldix is an algorithm that calculates protein stability and protein interaction energies. Foldix is the gold standard inside my area, because with the algorithm, once you use it on the structures you downloaded from the protein database, in addition to the various Perl, Python, and R scripts, you will get a large data set of values. This data is generated from the algorithm. So for example, in SARS-CoV-1, we generated almost 23,000 data points. SARS-CoV-2 was about the same, about 23,000. So I had 46,000 various energies. The computation saturation mutagenesis is a big term that means for the initial wild type amino acid end position, I mutated it to the other 18 amino acids to try and predict whether the mutations would either decrease stability or increase stability. Similarly, in our future work, it works for the same way for the protein-protein interaction. Now, what we have here, this is triple delta G. Triple delta G symbolizes binding affinity. So anything less than 0, you destabilize the complex. Anything greater than 0, you will stabilize the complex or strengthen affinity. Similarly, in stability-wise, you just decrease the monomer, the stability, or you increase the stability of the monomer if you have a positive number. This will become easier as I go along, and you will see the numbers we obtained from this study. Now, the major problem in protein research determining stabilization of protein-protein interactions. The reason why is majority of the tools that are free for scientists, they give very different magnitudes of destabilizing energies. For our study, we used the mutation, the folding energy to mutation minus the folding energy to wild type. In other studies, you will see this reverse, the wild type minus the mutation. The reason why we're doing it like this is because the FoldX algorithm dictates that we have the mutation minus the wild type. So I'm using the same protocol as what the algorithm suggested. You can also manipulate the algorithm furthermore to change this equation to the wild type minus the mutation. However, I'm still working on the script for that, but it's a bit challenging at the moment. So for this particular study, and our purposes, a negative value suggests that the mutation can stabilize protein. So negative value equals more stabilization. That's the big thing to remember. Positive equals very high destabilization. Now, in what you're seeing here is various analyses of the two structures. In A, I used a program called PyMol to align the structures to see what we call the RMSD, the root mean standard deviation. The greater the RMSD is less than 0, less than 1, the better the both structures are actually similar. So in this case, for our RMSD, our value was 0.69, which is extremely good. That is telling you, as we show in letter B, that the root mean squared, the correlation value is 0.82, which shows that the values of SARS-CoV-1 versus SARS-CoV-2 are very similar. Now I'm saying values, I mean the stability values in this case. In letter C, based on the values we obtained from the algorithm, remember I told you that each of them had 23 or 25,000 different values. We next decided to group it inside a pie chart to show which ones were highly destabilizing all the way to highly stabilizing. Now, as you can see, in SARS-CoV-2 and SARS-CoV-1, you had a lot of destabilizing in 2, but in 1, it beats it in the greatest destabilizing. However, if you go to the moderate destabilizing, which is 0.5 to 2.5, you see an increase in SARS-CoV-2 versus the parent of which is 32%. The neutral cases, which is negative 0.5 to positive 0.5, is we didn't really care too much about those values because they were neutral. So the understanding is neutral values do not cause mutations. Both structures had the same value for stability, and it's very similar for highly stabilizing. But for us is mainly the moderate destabilizing. You see an increase. What you see here is what we used R programming for. In R scripting, you can draw various heat maps, which is right here, in pie chart in line graphs, and we use the PyMol to show either the highest destabilizing or the lowest or highly stabilizing mutations. So what we concluded is you have your maximum, your minimum, and also your H2 variations. Now the H2 variations is what we discovered from the IGSMP and the NOMAD database. Inside African Americans particularly, the M82 and the S19 shows the greatest change in energies. Now, let me explain why. Serine is the wild type at the 19th position. Particularly when we change serine to proline, well, actually in this case it's a 0.97, which is in the same category as moderately destabilizing from the previous pie chart. M82, when it's changed to I, which is isoleucine, you see a great difference from the initial wild type to the mutation, which shows a very high destabilizing value for this position. Now, G326 is mainly occurring, you see a mutation inside the NOMAD that gives Latino Americans or Latin Americans. When the glycine is changed to the E, which is, I believe, aspartic acid, negative 0.2, which means you see a stabilizing effect. Now, the reason why we're looking at majority of the African Americans and the Latino or Latin Americans, we're trying to create a neutralizing peptide specifically for those two races, because what we're showing with the data is that the COVID-19 vaccine is not really doing the job it's supposed to inside the African Americans or Latino Americans. Thereby, you need to create more boosters in the long run for those two ethnic groups. Over here, what you see here is the M82, 561, and G46, causing the highest destabilizing energies. Now, green is the color of the ACE2, gray is the SARS-CoV-2, sorry. Similarly, green is also the ACE2, and gray is the SARS-CoV-2. And in both structures, the glycine at G561, 486, 268, well, particularly for us, these four were the highest for both complexes, causing the highest destabilizing values. As I said before, the 561, 483 are also there, causing the highest destabilizing, and also the D350 and the E370. Well, the D350 really is common in both, but you see the highest stabilizing values. Now, for these two variations, as I said before, in the African Americans, inside the SARS-CoV-1, instead of causing destabilization, you see either It's really a low destabilization occurring when the serine goes to the proline. However, when methionine goes to the isoleucine, we're seeing a 1.14, which is a similar to the SARS-CoV-2 complex. Latino Americans, you see a G326 going to the E. This is higher, which means that it's a greater stability. Usually in our study, stability, if you see a greater stability, it leads to a greater affinity. But that, currently we're working on that paper, and hopefully we should get it published very soon. Now, to compare our results, we use two other tools that they're free, technically, so to speak. One is the MCSM, which calculates stability energy, and the other one is a SAFEC sequencing, which is out of Clemson University. MCSM is out of Australia. Our predictions coincided with the top 5 mutations, which are all glycine, causing the highest destabilizing values across the board. Alternatively, well, you see the same case with the top 4 to 5 across the board. The genetic variance for the African and Latino Americans, this is the serine at the 19th position, predicted mutation at proline. Now, in the nomad allele count, first of all, the database for the nomad is about 30 gigabytes. So we had to filter out of 235 different mutations occurring. From those 235, I had to look for 5 that are showing the greatest destabilization or the highest stabilizing values. African Americans, which is the S19P, occurred in 45 of them. You'll see the difference in variation. I mean, in SARS-CoV-1, it was neutral. However, in SARS-CoV-2, you see a moderate destabilizing effect. K26R, which is lysine going to arginine, you see out of 528, 13 in the African Americans, 90 in the Latino Americans. And I should mention that AMR means admixed race. That's the term that they give Latin or Hispanic or Latino Americans in the United States. Now, there's not a real, in my opinion, I would say, because I've been doing this for a while, you cannot group certain people like that under one subheading. I mean, obviously, with the Latinx, Latino is very big, depends on the countries they immigrated from, to the United States and also to Europe. You also see the E37K, particularly in just one case in the African Americans. You see a big increase in destabilizing values. For stabilizing, the G326E, which was in African Americans, and the F40L, you see it going from neutral to close to a moderate increase in stability. Now, this is just the first part, what we are doing to show the stability values. By the end of the summer, we should also have published 2 more papers that shows the protein-protein interaction associated with the ACE2, the SARS-CoV-2 complex. And also, I've discovered 4 new positions on the Omicron variant that is highly cause a very large amount of mutations in this. It is not in the RBD particularly, it's actually in the RBM. So in the RBD of the ACE2 to SARS-CoV-2 is 130 positions. In the RBM is 90 positions. And out of those 90, I've identified 5 where you can see the greatest mutations that would occur in the future. And the prediction worked because you're actually seeing that in the new variant that just, well, I wouldn't say new, but a few months ago, the new variant that emerged in California. So our future findings, future work, design neutralizing peptides for stability, stabilizing the mutations. I continue to update Omicron mutations, and also see if there's a correlation between Omicron and the flu virus, which is coming up in the fall. I'm trying to see if it's the same positions being affected. And peptide design. We actually have a peptide being, with our collaborator, that's being verified inside the lab in the mouse models. So with that, any questions? Thank you for your time.
Thank you very much for your presentation. Does anybody have any question for him? How accurate is the model when extended to evolving, mutating strains?
That well, are you speaking about from the COVID-19 perspective or the ACE2 perspective? Because when you say evolving mutations, you're speaking mainly from the RBD of, for example, the Omicron or the RBM, and what effect that would have on the particular positions of the ACE2. If you're speaking about that, you're seeing a greater binding affinity of Omicron right now to specific receptors, which is actually at the RBM, which is very difficult to design targeted therapies for at the moment because there's only 90 positions. So in our lab, what we do from a structural biologist perspective, calculating and predicting changes in energy values. So that our theory is that, well, it's been proven too, that it greatly decreases the time for the wet lab to create new neutralizing peptides for specific mutations.
Great.
But a Pymol, I'm sorry, I'm actually answering a question from Dr. D. The Pymol, there is a very easy tutorial on YouTube. I mean, almost everything I've shown you here, YouTube has trained me for. The Pymol, the Python, the Perl, bash command to design the workflow. So I was on YouTube almost every day, just getting, learning how to apply the different bioinformatic tools. So if you, there's even different websites that you can actually see the Python code to actually draw the structure in Pymol. If you go to, just type in Pymol, then go to WikiLeaks, you'll see full tutorials on the web for that. You can also save the web pages. Actually, what I'll do, if anybody wants it in the chat, I'll just put it in the chat to help people with a Pymol. Any other questions?
Any question?
Now the protein interactions, it all deals with the specific protein database structure you download with. Before I forget, this is the link for to teach yourself PyMol and also all the various scripts in the categories. When you're discussing protein-protein interactions, there's two ways. One is structures that are experimentally verified, and the other is you can use something called the Swiss Pro repository. That will give you theoretical structures. Now, the Swiss Pro repository and also Google's DeepMind AlphaFlow, which just came out with theoretical proteins, you can actually compare the theoretical with the actual or the protein-protein interactions to see if you find similarities or differences. When you're trying to merge two different protein complexes, and you can't, if it wasn't verified yet, it's all theoretical. But my models that I use were also already verified by various labs using either X-ray crystallography, NMR, or some were even AlphaFold. The AlphaFold models came out later after we did this paper. So in the next two papers, you will see AlphaFold models more comparing the AlphaFold actually with the verified protein structures to see if there's a similarity of binding affinity or a difference. And we're using the Foldex to manipulate that also.